and I'm looking forward to the conference banquet, and I hope so are you. And let me start off by saying that I have an announcement to make. My talk is going to be succinct, and it will not take 20 minutes. So it's kind of joyful news. This work is a joint work with Nikita Yevseyev. This summer, we decided to join our efforts and to write another strikingly beautiful paper. So, in this title, you can see the words convolution and the roto-translation group. And I will say the RT group for short later. But I'm going to start off with Euclidean case. So, as you can see, the dimension of Euclidean space doesn't matter, and we can take the real line, let u and v be functions defined on the real line, and their convolution can be defined as follows. This integral. You know, the convolution have some important properties, and two of them...
something wrong on the left, I think. It must be y.
Must be...
You differentiate by, integrate by dx.
Of course, provided that the integral makes sense. Of course. The integral makes sense. Provided that the integral makes sense.
No, but the convolution is a function of y, okay? If you integrate the y over x, the convolution is a function of y. The first formula.
Yes, I agree. Here are some important properties of the convolution that are the commutativity and the possibility to change the sign of the derivative. So, in non-Euclidean settings, for example, in a case of Carnot group, this is the standard definition of Carnot group. Perhaps you all know this definition. In this setting, we have the following formula for the following expression for the convolution. This is pretty the same formula, except that instead of the minus sign, we have the group operation and the operation of inverting the element. So, unfortunately, sadly, the previous properties, the properties mentioned above, do not hold in such a setting. In general, the commutativity is not valid, and we don't have the possibility to change the order of differentiation. And the most important property, the property that we will refer to, that we will address in this talk, is the third property. I want you to pay close attention on the third property, because we're gonna have to deal with this property later. However, because of the left invariancy of the vector field x, we have the last equality. So these relations can be established by taking the derivative under the integral sign. if you remember the last property in Euclidean case, there were two equalities. There were three equalities. Yes, three equalities. So only the last one is fulfilled. In Jefferson's paper, that is called the Poincare inequality for vector fields satisfying Hermander's condition, in Duke Mathematical Journal, Jefferson proved that instead of this equality, we have the following assertion. So you can see the difference. Here we, instead of v, we have the derivative of the function psi, and instead of xu, we have the sum of horizontal derivatives, of the horizontal derivatives of the function f. So our goal in this work is to establish some analog of the last proposition for the roto-translation group, the RT group. The roto-translation group is the group of orientation-preserving motions of the Euclidean plane, and an element of that group can be written in the following matrix form. Here you can see the part that corresponds to the translation, and the part that corresponds to the rotation. And the basis left-invariant vector fields can be written as follows. So I want you to note that we don't have the nilpotency and the homogeneity. These are the properties that were true for Carnot groups. So, as I said, we don't have the equality right here, and Jefferson's idea to establish some analog of that equality is to obtain for a given vector field x a vector field y, so that we have such a relation. Unfortunately, I don't have a light. I have it, yes. We have such a relation. In the case of the RT group, this relation have the following form. If we have a function f and a psi, a function that is infinitely differentiable, and have a compact support, then we can find the vector fields x, y with tilde such that this equality is true, and the specific form of those vector fields are as follows. We can establish this specific explicit form because of the, of course, explicit form of the horizontal vector fields on the roto-translation group. But you may ask why we chose the roto-translation group as the subject of our research. So I can give some reasons for that. First of all, nearly a year ago, I defended my thesis, standing right here, and in my dissertation, I had to deal with the roto-translation group. So I showed that the theory of mappings with bounded distortion can be extended to the roto-translation group. And I believe that's quite interesting to develop further those research and to establish new properties for the roto-translation group. And the second reason, and actually this is the main reason for that, is You know, the roto-translation group became one of the main tools in analysis, namely in process of image perception in the human brain. Over the past 10 years, a number of articles, a number of papers have been published where the RT group found very wide application, and you know, the image formed on the retina of the human eye, this can be mathematically described as the convolution of the input signal coming from the outer world with some Gaussian kernel. So that is why we are so curious about the properties of the convolution on the RT group. So the main reason is that the RT group is used in image perception, in modeling image perception in human brain. Using the last lemma, we can prove the following theorem. Suppose that f is a function of class C1, and psi is an infinitely differentiable function with compact support. Then we can find differential operators, such that the following equality holds. What is interesting in this equality? First of all, the index I runs over 1, 2, 3, but x3, the derivative that corresponds to x3, can be expressed only in terms of horizontal derivative, x1 and x2. And in the course of the proof, we obtained the specific form of the operators d1i and dy2. I don't think that this specific form are good looking or attractive, and on a number of occasions this explicit form is unimportant, but if we need that form, then here it is. So, as I promised, I'm done. That's it. Thanks for your attention.
Very much for short talk. Any question? Let me some remark. Convolution is very important because there is one-to-one correspondence. Let's consider, for example, G groups. So there is one-to-one correspondence between left invariant sub-Riemannian or Riemannian metric and symmetric Gaussian convolution semigroup, one parameter semigroups with absolute continuous probability measure. And density of these probability measures will depend on t, time, parameter, is satisfied the sub-elliptic equation of type of like the heat equation. If we have Riemannian metric, then we get usual